Hi, folks. This is Heath. We're not covering new material today, but I thought I would record some comments about the practice test and work through a couple of questions. Let's get started. All right. So this is problem one off of the practice test. The concept is the definition of a crypto system. When I mean the formal definition, I mean what are the 5 parts of the crypto system, and then the roles that Alice, Bob, and Oscar play. In this sample problem, Alice and Bob have invented this algorithm for encrypting messages, where she shifts the character X by the number of times that the character has appeared in the plain text so far. So the first time that S appears, for example, it gets shifted one place and becomes a T. Then the second time the S appears, it gets shifted twice and becomes a U. And the third time the S appears, it gets shifted 3 times, TUV, and now it becomes a V. Then the next time it becomes a W, then the next time it becomes an X. And this, I think, should be a Y, right? Yeah. Because I messed that up. There you go. So that should be a Y. And then this one over here then should be a Z. And then this one should be an A. So I've messed up the encryption in the practice test. I'll have to go back and fix that later. But the question is, why is this not a true crypto system? We can specify what the plain text characters are, the ciphertext characters are. There's really only one key. It's this algorithm here. But here's the problem. A crypto system requires that the decryption of the encryption of any letter gives you that letter back. That means the encryption function, has to be invertible. But the problem here is that the plain text I'm just going to write the first 4 letters of the plain text. S becomes T, H becomes I, E becomes F. S is showed up a second time, so now it's U. Encodes exactly the same way as the plain text. You can see this coming here. SHE and then T. S becomes T, H becomes I, E becomes F. And since T has appeared the first time, it encodes as a U. And so Bob, having received these 4 characters, doesn't have any way of knowing which plain text that corresponds to. Bob might guess that she sells seashells makes more sense than she tells seashells, but the point is that the decryption algorithm, the encryption algorithm is not one-to-one. And therefore, we cannot guarantee that the decryption algorithm will give you X back. If Bob decodes this as S, he could be wrong. If Bob decodes it as U, he could be wrong. And so we don't have a guaranteed way of being able to decrypt this message. And so it's not a crypto system. Shift cipher and substitution cipher, I didn't put any practice problems for these because I think the shift cipher is easy enough, you don't need any. Substitution cipher, I mentioned on the instructions that I'm not going to give you a problem to decode that requires guess and check on a test. That's one thing to put on a homework when you have a whole week to work on it. It's not something I would put on a test. I might ask you to describe the substitution cipher or do something, but you're not going to have to do anything major with this topic. So let's move on. Excuse me. All right, so let's use the extended Euclidean algorithm to find the inverse of 11 mod 16. Let's do this problem first. Okay. So the first thing is we're going to do is divide 11 into 16. And that goes one time with 5 left over. Then we go 5 goes into 11. That goes in twice with 1 left over. And then 1 goes into 5 times with 0 left over. We'll need these 3 numbers here because when we do the extended part of the algorithm, we see the extended part with a 0 and a 1. 0 minus 2, or 0 minus 1 is negative 1. This calculation is 0 minus 1 times 1. And then the next term is 1 minus negative 2. It's 1 minus negative 1 times 2 is equal to 3. And this last number is the inverse. 11 inverse is congruent to 3 mod 16. We can check this by multiplying 11 times 3. We get 33, and 33 is congruent to 1 mod 16. Because 33 is 32 plus 1, and 32 is an exact multiple of 16. All right. So now that we have the inverse of 11, we can solve this congruence here. Solve 11k is congruent to 5 mod 16. We're going to multiply both sides by 3. On the left side, we get 33k. On the right side, we get 15. But 33 is congruent to 1. We saw that up here. And so we just get k is congruent to 15. All right? And we can check this also. 11 times 15 is 165. And that is congruent to 5 mod 16. Because this is 160 plus 5, and this is an exact multiple of 16. All right, let's move on. So let's look at the affine cipher. Suppose for some affine cipher, the encryption of C goes to R. So C goes to R, and K goes to P. That means that 3 goes to 18, and 11 goes to 16. And so what this is telling me is that 3a plus b is congruent to 18 mod 26. And 11a plus b is congruent to 16 mod 26. All right, so if we subtract, what ends up happening here is that we get 8a is congruent to negative 2 mod 26. Or 8a is congruent to 24 mod 26. Now, 8 is not relatively prime to 26. This is a problem. And so this congruence will either have no solutions or it will have multiple solutions. And in this case, it has multiple solutions. And one of them is 3. We can tell just by looking. 8 times 3 is 24. The other one, I think, is 16. 8 times, let's double check this. 8 times 16 is 128, which is the same thing as 104 plus 24. And 104 is a multiple of 26. It's 26 times 4. And so we have 2 possibilities for A. But the affine cipher requires that A has to be relatively prime to 26. And 16 is not, but 3 is. So this is a little tricky. We have 2 possibilities for A. Possibilities for A based on this congruence. A is congruent to 3, A is congruent to 16. But the GCD of 16 and 26 doesn't equal 1, and so A has to equal 3 by elimination. So now we know what A is, we could go back and figure out what B is. So then 3A plus B is equal to 18. So 3A plus B is congruent to 18. So 3 times 3 plus B is congruent to 18. That's 9 plus B is congruent to 18. So B is congruent to 9. We could check that with the other one. 11 times 3 plus 9 is 33 plus 9 is 42. And 42 is 26 plus 16. And so that's congruent to just 16. And so that checks with this one also. And so our key is A is equal to 3 and B is equal to 9. But we had to do a little bit of work to get A. All right. Encode the first 3 words of this sentence using a Vigenere cipher with the keyword crypto. All right, so if we encode the first, and then underneath it write crypto over and over again. This is the same thing as, this is going to be 5 and 3. This will be 14 and 18, 3 and 25, 15 and 16, 4 and 20, 5 and 15, 20 and 3, 18, no, 8 and 18, 5 and 25, 6 and 16, 9 and 20, 18 and 15, 19 and 3, 20 and 18. So 5 plus 3 is 8, which is an H. 14 and 18 is 32. 32 minus 26 is 6. 6 is an F. 3 and 25 is 28. Minus 26 is a 2, which is a B. 31 becomes an E. 4 and 20 is 24. 24 is an X. 5 and 15 is 20. That's a T. The next word is 23, which is W. 26, which is 0, which is a Z. 30 is a 4, which is a D. 6 and 16 is 22, which is a V. 29 is 3, which is C. 33 is 7. 22 is V again. We got V in two different ways here, F and P and S and C. The Vigenere cipher is not a monoalphabetic cipher. This can happen, and that's actually kind of good. Finally, 20 and 18 is 38, which reduces to 12, which is an L. I hope I did that okay. Let's move on. The Kassiski Test. We've got a long string of ciphertext that was encoded with the Vigenere cipher. And somewhere at position 5, we had the letters APO. And then later on, way down at page position 45, we had an APO again. And so these were 40 characters apart. And then 5, 6, 7, 8 would be HKY. But then way down here at 83, we had an HKY again. And these are, from 8 to 83, 75 characters apart. If these are the only repeated trigrams in the ciphertext, suggest a plausible key length, we might want to try a factor of 40 and 75 first. And the GCD of 40 and 75 is 5. And so that's what we would try first. Now, it's always possible that a trigram could be repeated just coincidentally. We saw an example of that one time. But the odds are much greater that the repeated trigram is indicative of a pattern in the Kassiski test, in the ciphertext. All right. Let's look at number 7. What is the index of coincidence for written English text? Approximately 0.067. Let's try an index of coincidence for this text. So we have 3 letters. K shows up 1, 2, 3, 4, 5, 6, 7 times. O shows up, change colors for this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. And Z shows up 1, 2 times. Right over there. This is a total of 22 letters. I'll double check. That would be 4 plus 3 plus 2. That's 9 letters in the top row. 4 and 3 and 6 is 13 letters in the bottom row. 9 and 13 does add up to 22. Okay. So these counts I'm pretty comfortable with. The index of coincidence is 7 squared minus 7 plus 13 squared minus 13 plus 2 squared minus 2, all divided by 22 squared minus 22. So 49 minus 7 is 42. 169 minus 13 is 156. 4 minus 2 is 2. 484 minus 22 is 463. Is that right? Squared is 484 minus 22. Nope, 462. You'd think I could do math in my head, but there we go. Let's try that. All right. So 42 plus 156 is 198 plus 2. Is that actually going to be exactly 200? Is 200 divided by 462. All right. We're going to do one more today. That'll get us to the halfway point. And then we can look at some more problems on Friday. So, give a reason why a hill climbing algorithm might fail to converge to the correct key. And so the idea was this idea that we'd seen before, where this is the correct key, and this is the current guess. And no minor switch in the key is going to take us from here to here. All the minor switches take us to lower points on the same hill. And therefore, making a switch of a couple of characters in the key doesn't increase the metric that we're using to test our decryption, but and since we're using a greedy algorithm, we reject all of the changes to the key, but we are not on the hill where the correct key is. So trying to put that in words for the first sample problem, it is possible for an incorrect key to be a local maximum such that, let's say for an incorrect key K, such that any small modification K prime results in f of K prime being less than f of K. And since f of K prime is less than f of K, since f of K prime is less than f of K for all modifications, the algorithm never rejects K, even though K is incorrect. The way that we addressed this problem is to intentionally make the algorithm a little bit less greedy so that there was a chance of dropping off of the hill and onto another hill. And so the solution we used was what we called simulated annealing, where we strengthen the algorithm by actually making it a little bit less greedy. And then the second part of the algorithm is to describe the log quad test. So the idea here is that the log quad test is an alternative to the index of coincidence. it is a measurement that we can compare how close a sample of text is to true English. It measures how close a text sample is to true English. So we have a sample of text. If the index of coincidence is about 0.067, that's a good indication that that text has been correctly decrypted. If the log quad test results in a large value, that's a pretty good indication as well. The way the log quad test is it sums all of the frequencies of the quadgrams. So over all of the quadgrams in the text. So sums the frequency of the quadgram sums I. In theory, it actually sums the logs of the frequencies instead of the frequencies themselves. That keeps the numbers within a more reasonable range and helps prevent underflow on a computer. So that's how the log quad test works. All right, so this is not all of the practice test yet. This is some to get us started. If you have questions, post them to the board. Get in touch with me. Come by class today, or show up for my office hours tomorrow. We'll look at the rest of the practice test on Friday, and good luck. Y'all take care.